FunMat-II is a competence center in functional nanoscale materials based at Linköping University. With a team of more than 40 academic and industrial researchers coming from 2 universities, 2 research institutes, and 8 industrial partners, we have a wide competence within material science and surface engineering. We focus on wear-resistant coatings for cutting tools, corrosion-resistant coatings for fuel cells, and catalytically active materials for batteries. Using a combination of experimental and theoretical approaches, we generate knowledge on synthesis processes and material behavior in specific applications.
This is Jessie, our magnetron sputtering deposition system at IFM. It's one of the workhorses here in the thin films division. It is equipped with 4 magnetron sputters and works at a base pressure of -9 torr. Jessie is used for growing thin films, mainly metallic, nitrides, oxides, and borides. One of the specialities of Jessie is that it is equipped with a solenoid coil around the substrate holder, which helps in attracting more plasma towards the substrate for denser coatings with better properties. Jessie can be operated on DC, RF, and pulse DC mode. In our project, we use Jessie for depositing high entropy alloys, or more commonly called multi-component alloys.
Hi, welcome to Verdandi. So this is another one of the magnetron sputtering deposition systems that we have for FunMat. So this sputtering system is equipped with 4 targets, and all of them are run by DC power supply. One of the targets has a stronger power supply, so we can choose a wide range of metal targets for growing different kinds of films. So for this deposition system, we plan to grow high-quality epitaxial nitride films, which we will then characterize for elastic constant measurements. Such examples are titanium nitride, chromium nitride, and zirconium nitride. And we also plan to grow ternary nitrides like titanium aluminum nitride for studying defects of hard nitride films.
Hi, this is a single-source DC cathartic arc system that is in our division. Its name is TOR. So here we are using a 100mm source that have which has been used the same in the industry. So the configuration here, that on top is our source and at the bottom is our substrates. On the other hand, in this configuration, we can also exchange our substrate stage to any other plasma diagnosis technique, like the mass spec spectroscopies. And in order to, for people to work safely, we build up the stage that people can stand here confidently. And on top here, we can see that this is the DC single source that we've been using. And it has the same design in the industry. That means that this system also have the capabilities of mimicking the industrial environment. With this single source DC cathartic arc system, we normally produce hard coating like titanium aluminum nitride or titanium nitride for our need, and also to see the plasma generation from this source.
Another deposition system available in FunMat-II project is called Samsung. Samsung is provided by our industrial partner, Chemical. It is a commercially available magnetron sputtering system. In this system, there can be up to 6 sources mounted, and in the middle, there's a high pimp source. High pimp stands for high power impulse magnetron sputter. We also have the capability with the multiple fold rotation simple stage, which we can apply different bias. We use Samsung for plasma and film growth studies in the project.
Hello, please come in. Hi, I will show you around to give you some information about this chemical lab. The lab is equipped with 2 film hoods, and as we can see here, this one, you can do the synthesis at high temperature. Now on this side, we have the balance and ultrasonication bath and oven bottom here. Here would be another hood, and it's for the lower temperature. Let's move to another side, and there are 2 characterization equipments, and this one is TJDSC. You can do some studies by the equipment, and that would be allow you to approach to some information about the phase transformation and the composition of the material. Here it's a phase solution called SP2020 from Micromagnetics, the company. You will get some information about the surface characteristics, such as BET surface area and pore size and pore volumes. And besides that, actually you can also do some chemical solution. Those are 2 different types of balance which could meet the different needs in the lab. And yeah, that would be all information. Thank you.
Welcome to the laser lab. Before you enter the laser lab, you need your goggles, because I'll switch on the laser and we should have them on. Welcome to the brilliant light scattering setup that we have. So this experimental setup is used to measure the acoustic phonons in a sample, and these phonons will help us in the elastic characterization of materials. The final ultimate goal is to get elastic characterization of the hard coatings that we have, that we fabricate in the group. So I will switch on the laser, and I will request you to have your goggles on. Right. Yes. So what we have here is a single longitudinal mode laser. Okay. And we have a lot of optics that will guide the laser to the sample, and we collect signal from the sample. The laser travels through a lot of optics here, and there are certain things that you can do with the optics, like change the polarization and change the angle at which the laser is incident on the sample. So all these optics help us to guide the laser, and then the scattered light from the sample is our signal. This is what we detect using this detector. The scattered light will be measured at different angles of incidence and different polarizations of the laser, and where the scattered light is collected by a lens here, and then it is collimated by a lens here, and ultimately with this range of optics it is focused onto the pinhole of the detector. So the signal reaches the pinhole and it enters the interferometer here. So what this interferometer does is 2 things. It has high contrast, and it is highly selective in its spectral regime. So after the signal reaches this, it enters the interferometer. And an example of data that we collect is shown here, and what we have, these 2 are the Brillouin shifts, and this is the laser line. So we use this Brillouin shifts to measure the acoustic wavelengths, acoustic velocities, and in turn get the elastic constants of the material.
Hey, welcome guys. Come in. We are just discussing a little theory here about BLS. So this is the spectra you see, what we have to actually put into our equations here. So the spectra we have here shows the phase shifts in frequency, and these frequency shifts will be connected to the discussed wave velocity of the surface acoustic wave. Yeah, we have discussed it here. So, but now my wish is to model it a little bit simplified starting point. So what do we have? So we have a crystal, yes. We have an incoming light by the laser, yeah. And then we have a backscattered also. But we have a material setup here we have a normal surface normal vector which is connected to the crystallographic direction. Now we can assume that you have a cubic material. Yeah, that's a cubic material with particular elastic constants, and then the sound wave will generate the surface acoustic wave. Here will run. Now, if you assume a certain crystallographic orientation, we take the simplest one, one direction, and we take an orientation of the wave, incident wave. You have seen already in the lab. So the simplified case is the following. Then, so top view, the incident light coming with a Q vector, or K vector, we can call it. And that defines also the crystallographic orientation. It can be, again, the 1 or O in this case, let's say, that's the X direction. And then you put all these K vectors and crystallographic setup in the equations, and then you can get out the sound velocities. Now my question is, what do you think? What happens if you actually change the incident angle? If your laser is coming with a different angle?
Yes, actually we performed this in our lab, and here you see that for silicon case, with the angle of the incidence, the peak position is changing, and that we can confirm with our theory.
Yeah, that's right. So this should be the case for a surface wave. Oh.
Yes, we can relate it with the theoretical part and the experimental part.
Right. So can you do the modeling which I asked for you to set up this small system, simplified case?
Yes, I can
and check this movement also.
Yes, I can confirm it and calculate the velocities for each angle of the incidence individually.
So, do you have anything to report about?
Yes, I started with the theta is equal to 60 degree, and I calculated the elastic constants. So first we extracted the Brilliant shifts from our experiments, and then I did some calculations for the velocity, and then eventually I extracted the elastic constants for silicon C44 and C11, and they agree quite well with the literature values.
That's very good. That's promising. Thank you, guys. So we left behind us the BLS experiments and the analysis. Now we can ask my colleague about simulations on hard materials. Follow me. Hi, Davide.
Hi.
So, nice to see you here. Do you have any results concerning some toughness in your recent simulations, please?
Yeah, I was looking at this, the behavior of this material when you pull it. This is a hard material, and one would expect it to break suddenly when you pull it, but instead, look what this does. You pull it, and then it transforms in this way. It's a bit like a spring behavior.
Wow.
It's really surprising.
It's interesting. Yeah.
And then you can see that behavior here in this what we call stress versus strain curve. That you pull it, and then it transforms here, and then it withstands a huge elongation. It doesn't break.
It's long. Yeah.
And then from this
0.5 is it's 50%.
Yeah, 50%. Mm-hmm. This is of course an ideal situation where you have no defects in the crystal. And then from this kind of curves we can get the classical elastic constants from the slopes of these curves. We can calculate this with some scripts we have.
Are these data already on our database, or you have to upload it?
No, these are data that will be uploaded on the dataset because these are calculated directly with the vibrations of the atoms, and so they provide additional information compared to what we have in static calculations.
Right.
So you see things that from these kind of calculations that you wouldn't see in conventional calculations.
X-ray diffraction, or XRD in short, is a non-destructive analytical method that is commonly used in the research. Here at IFM, we have several access to different configuration diffractometers. With different configuration, different measurement can be performed. So for example, for a theta-2 theta scan, it can provide us the information about the crystal orientation in the film coating. By changing the lenses and the receiver with the right configuration, other measurements can be performed. For example, grazing incidence, XRD, stress measurement, and pole figure. Here at IFM, we have the capability of doing so.
So here, this is the FIB, is a focus ion beam machine. Actually, we have a double system. This means that we have SEM and a FIB together. Focus ion beam means that instead of we have a beam of electrons, we will have a beam of ions. And these ions come from a gallium source. Here we have a model of a cutting tool. Then in this project, I want to analyze the crater region that is in the edge. But in a real sample that looks like this, it's very, very small. It's here. So then we need FIB to see in a very, very small area to get a lamella in the middle of the crater region. So without the FIB, I would not be able to do the investigation of the wear in this area.
The scanning electron microscope is one of the workhorses here in IFM for initial material characterization. By using a beam of electrons and detecting the scattered ones, we can image a thin film sample and know its morphology, thickness, and its various features. The TEM is another powerful microscopy technique where a beam of electrons is transmitted through a very thin specimen to get an image. With this technique, we can see crystal structures at very high magnifications and atomic scale resolutions of thin film samples.
Mechanical properties, for example, hardness can be measured by nanoindentation. This technique is based on the use of a diamond tip, which is indented into the sample with an increasing load to the maximum indent load, result in the residual area of the imprint from a load versus displacement curve during the nanoindentation measurements. The hardness can be then calculated. Hardness is one of the most frequently used properties for evaluating protective coatings. Coating with higher hardness can have a longer lifetime and a better performance during the cutting application. Other mechanical properties like elastic constant can also be calculated from software.
For more information about the center, visit our website at www.funmat-II.se and follow us on Instagram.